Good afternoon. Many thanks for introduction. Many thanks for invitation here. It's a great pleasure to be again in Osaka and to give this lecture. This lecture will be very similar in content to previous lecture. You will hear the same words, super exchange, double exchange, but you will see how the same thing can be in physics presented completely differently. Don't afraid, it's not using something, same word for the different physics. Physics is similar, but one can, of course, in physics always explain the things in different ways. And it is often a matter of taste, which explanation is better, which is more intuitive. So the plan of my talk is outline show here. I will start from very basic preliminaries. Anyone in the audience heard several times that, but just for completeness, I will discuss it. Then I will move to what we call potential exchange, which is very important to understand the simplest case of ferromagnet is an iron, in principle, the simplest. And then kinetic exchange, which leads us to Kondo Hamiltonian, double exchange, indirect exchange between localized spins, which can go through free carriers in the bands or can go through valence bands. So starting from these preliminaries, well, as was said, we have very complex system, many electrons interact with other. And so we have Coulomb interaction, but also, and this is very important, remember that if you have Schrödinger equation and you are very clever, you solve it, you have wave function, energy, don't stop. Remember that there are boundary conditions. And one of the important boundary conditions is that if we have fermion system or identical particle with spin, which is fractional, 1/2, 3/2, and so on, the wave function must be antisymmetric. So only solutions which are antisymmetric against permutation of the electrons are good solution of your problem. So you kick out solutions which are not filling up this, which solve Schrödinger equation but do not fill up this condition. You have to reject them. And then you see immediately if it is true, if you put two electrons sitting in the same place, the only way to make that we have the same wave function, because then this wave function will be identical to that one, and to be equal to their minus function, it must be 0. So what that says? It says that two electrons cannot meet. Probability of finding two electrons in the same region of space is just 0. And this introduces, together with Coulomb interaction, correlation. Electrons does not move independently, but their motion is correlated. They try to avoid themselves for two reasons. One is this Coulomb interaction, they simply repulse. But if they have the same spin in addition, because this argument somehow it's assumes that we have the same spin, they try to avoid each other as well. Yeah? There is statistical forces which induce or force the electron to be far away. And then what is another preliminary important information which anyone knows, but again we should repeat it, that very simple, it's kind of classical, that we have nucleus and we have two electrons on them, like hydrogen minus particle. We have change of binding energy. We have single electron binding energy is Rydberg, but if you put second electron, the second electron is repulsed by this one, not only attracted by the nucleus, and altogether makes that difference between binding of single electron is much higher than if we have second electrons, the binding energy much different. And the difference between the two is the famous Hubbard energy U, which anyone is familiar with. But this is also important, of course, in all magnetic materials. Hund's rule come out of that and so on. But for us, important is that if you have transition metals in semiconductors, if we have, for instance, manganese with 5 electrons, and if you want to put 6 electrons, it have much higher energy. And this makes it actually here, we have a lot of room. This is 13 electron volts. We have a lot of room to have here s p-type bands. So in solids, actually electron does not go here, but cannot go here, stay here, and we end up with half-filled bands. Yeah? These bands stay half-filled. We can put 10 electrons, but this electron does not go here because this electron will stay with 6 electrons much higher in energy. And we end up with local moments. And another thing, we speak about magnetism, so now we have the spin. We said that the spin exists as unfilled bands because of this repulsion between electrons. But now we ask the question, what is interaction between the spins? We know that we have ferromagnets, anti-ferromagnets, and we ask the coupling about the origin of the coupling. So the talk will be about origin of coupling between spins, how two spins are coupled in solids. And very important things which is shown here is that we have coupling which is like two magnets. If you have two magnets, probably you played in school or you play with your refrigerator magnet, that they want to be, and north wants to be south pole, and south pole wants to be close to north pole. We have dipole-dipole interaction between the magnets. And this is just school-type interaction between two dipoles described by this well-known formula. And important things to realize that this is important in some cases. It's very important to understand domains, important to understand the magnetization, to understand the PR line widths. But if you put numbers, the interaction at short distances is much, much too small to understand ferromagnetism solids or anti-ferromagnetism solids. So never forget about this dipole-dipole coupling. In many cases, it's very important, partly because it's short range, it decays very slowly with distance, but it's too weak to explain the coupling between the spins. So we have to go to quantum mechanics, as Dirac did, Schrödinger, Heisenberg did, and then we can understand why two spins prefer in some cases to be parallel, in other cases they prefer to be anti-parallel. So the question is, what is the source of this coupling between the spins? Why one is positive, another type system is negative? What is physics behind this chain which couples two spins? And let me start again from a very general statement that, well, if you speak about energies, we can always recall or remember that in Hamiltonian we have potential kinetic energy. So we ask now the question whether potential or kinetic energy depends on orientation of spins. So we ask the question whether the dominant effect is that, for instance, for one orientation of the spin we have lower potential energy, we have deeper well for one orientation of spins than to another, or there is maybe kinetic energy involved. We all know that kinetic energy in quantum mechanics, not in classical physics, in quantum mechanics, is derivative of the wave function. Which means if we have strongly localized wave function, kinetic energy is large. If we have delocalized wave function, kinetic energy is low, because it's derivative of the wave function. So we ask the question whether our electrons, or what changes with this orientation of spin, maybe it's kinetic energy, that we have wider potential well in one case, and then lower the 0-point motion, this kinetic energy, or maybe for another we have higher. And this we call kinetic exchange as this potential. We will discuss a little bit about physics behind why we have one Z, but the name comes from that once we play with potential energy in Hamiltonian, another case we play with kinetic energy in the Hamiltonian. So now we go to the physics of this exchange coupling, and first we discuss situation. We have carriers in this band, and we ask the question, what is the coupling between carriers in the band? Then we will discuss what happens if we have localized spins and carriers in the band. And then we will ask another question, what happens if we have no carriers? We have an isolator, a wide gap semiconductor, and we have only localized spins, and what can be mechanisms which couples the spins together? So we start from this potential and kinetic exchange, and then we will discuss how this goes. So we start now from this potential exchange. We try to understand more details this potential exchange, and this will bring us to these various situations. So what about this potential exchange? How we can understand that? Potential exchange, actually we can go already to helium atom to understand that. What is the origin? And we said that it's a very important Coulomb interaction. We have Coulomb interaction and we have symmetry of the wave function. So let's assume that we are interested now in potential exchange or exchange coupling between two spins in helium atom, assuming that one of the electrons is in S-type state, 1s, another in 2p states. It's excited state. Why we are interested in excited, not in ground state? Because in ground state, we know that these two electrons have to have opposite spin. So we ask the question whether ground state will correspond to this electron parallel, or maybe it will correspond to anti-parallel. And we want to use perturbation theory. Very simple, the simplest. So what perturbation theory says that let's try to forget about interaction between electrons, but ask the question, what are eigenvalues and eigenenergy without interaction between electrons, and try to construct wave function from this anti-perturbed wave function. So if we forget about interaction between electrons, the wave function is just, we have sum of two Hamiltonians. This corresponds to one electron, this corresponds to second electron. So solution would be a product of the wave functions. That first electron, for instance, is this 1s state, the second is this 2p state. But such a wave function will not be antisymmetric against permutation of the electrons. We have to take something which maybe another combination, some kind of combination, and to have this antisymmetric wave function. Another combination will be that first electron is in p state, another electron, second one, is in 1s state. Since this is solution of the Schrödinger equation, this is solution of the Schrödinger equation, or the combination of this two is solution of Schrödinger equation, and in addition we put minus here, permuting position of this two electron, we have antisymmetric wave function. So we rejected solution as Z1, we rejected Z1, but we took the combination because only this combination is antisymmetric against permutation of the electrons. And now having this wave function which fulfills boundary condition, we use perturbation theory to calculate what is the expectation value of interaction, Coulomb interaction between these two electrons. But now we have to be very serious about spin. We should not forget that electrons have spin. And then we have to say, okay, the wave function should be antisymmetric. So maybe it would be that spin part will be antisymmetric, or then orbital part must be symmetric, that total wave function is antisymmetric, or we have to take antisymmetric orbital part and symmetric spin part. And as you see, this corresponds to what we call singlet. This expectation value of total spin is 0. Here, expectation value is 1. So we have situation where we have total spin 0, and actually this electron exchange their position, we can naively say, or we have another solution which corresponds to two electrons parallel. And we have free states because electrons can be up, electron can be like that, electron can be like that, the projection of spin. So we have three triplet wave function and one singlet wave function. So you see how without introducing any magnetism, any magnetic interaction, just electrostatic, and using this anti-commutation, this change of sign when we permute the position of the electron, we end up that wave function, total wave function, is spin dependent. Somehow spin dependent comes into play. And now we calculate expectation value of energy, and we end up with this kind of equation that we have energy of one state and energy of second state, repulsion between these two electrons, this U, and this exchange we are interested in, which has different type for singlet and different type for triplet. Why this Coulomb interaction differs for these two type of states? Because remember, in case of triplet, if we are in case of triplet, we can come back. If we are in case of triplet, probability of finding two electrons nearby is 0. So it means Coulomb interaction for triplet is reduced because electrons never meet. So if you calculate expectation value of Coulomb energy is lower because electrons never meet. By contrast, in singlet, they have different spin. They can meet, and they have this symmetric wave, orbital wave functions. They can meet, and therefore the Coulomb energy is higher, because they are stronger, repulsion is stronger. So altogether means that this singlet state has actually higher energies than this triplet state, because this J actually one can show that it's always positive. And important, very important things here, related to what we discussed in previous lecture concerning this short-range versus long-range interaction. Please note that if we have this repulsion between electrons, and assume that these two electrons are far away, and their orbital wave function is delta functions, that they are localized in two regions of space. If we take that they are localized in two different regions of space, if you can calculate integral of this interaction between electron with this delta function, you will end up with this position of the first electron, you can interact around the position of the second electron, and you will end up, shortly speaking, just energy corresponding to Coulomb interaction between two electrons, yeah, which is 1/r. So it's a reasonably long range. It's decay very slowly with distance. But if you do the same with this Fock term corresponding to this difference between energy of single and triplet state, now if you want to integrate over r here, if you integrate over r here, and if you have delta function, as we said, position is delta function of this two state. So if you integrate over that, you will have 0, because this will correspond to completely different position of the electron. Yeah? That electron one state and different state are very far apart. So you will end up for a distant electron with no overlap of the wave function, you will end up with 0. So exchange is very localized. Goes to 0, exponentially goes to 0 if overlap between wave function decreases. Yeah? So it's very, very important fact, and somehow makes that, despite that Coulomb interactions involved, exchange is short range. It requires either the localized electron or delocalize something which mediate interaction. If there is no something like that, interaction is 0 for electrons which are far apart. And then we can cast everything here into this famous Heisenberg form, spin times spin. You can play with spin matrices and show that this is the case. So summarizing, this was about atoms. It could be in quantum dots as well. If we have two electron different states in one quantum dot, then typically there is potential exchange between them. Coulomb interaction is involved, and this Coulomb interaction, this potential term in this Coulomb interaction makes that this electron wants to have spin parallel. Electrons prefer to be in ferromagnetic state. And there are many, many, of course, consequences. One, if you go to atom, that if you now take this manganese atom with 5 electrons, and you take S now state, you can do the same with wave function, and you can convince yourself that the ground state will be ferromagnetic. And difference in energy correspond to exchange integral in manganese, which is 0.4 eV. If you go to 4p 3D interactions, a little reduced. You can do the same with europium, go to tables and find that G for S electron interacting with here 7 electrons of F electrons is smaller for S type and is bigger for D type. One can easily understand why, because wave functions are very localized of D electrons, so only of F electrons, only D electrons have reasonable overlap. This have smaller overlap, so this is smaller. But also important is now we go to semiconductor. We have many S-type carriers, or even if we have single, but the single electron is localized on many, many cation sites. So now electrons can interact, being delocalized on different sites, can interact with many manganese spins. So you can see that from the viewpoint of this electron sees something like molecular field acting on this electron, yeah? Because at the same time it interacts with many spins. There is kind of molecular field. If you go to Pauli Hamiltonian, spin Hamiltonian of free electron, it's G times field times spin of electron. So this would be this molecular field which enters to this formula. Yeah? So we can say we have kind of molecular spin acting of spin of the electron. We have splitting, which will be proportional to number or concentration of spins we have, the localized spins, and average value of spin, which average value would depend, if there is no interaction between the spin, just on temperature magnetic field. We put strong magnetic field, spins will be polarized along the magnetic field. We put small magnetic field, for non-interacting spins we will have 0, because all orientations equally probable, so expectation value is just 0. And this is seen experimentally. We do experiments. We measure spin splitting of the conduction band by Raman scattering, for instance, we see that spin splitting somehow depends on the magnetic field, and then to saturate at low temperature, because all manganese start to be saturated. And if you calculate what is the magnitude of the spin splitting, what is the effective lambda factor, we change magnetic field, we have splitting. This magnetic field polarizes manganese spins, but we can say effectively we have kind of G factor, electron has effective G factor. This G factor of low temperature is about 500. So this coupling to manganese spins hugely enhance splitting of the electrons in semiconductors, yeah, by several orders of magnitude often. And this is purely due to Coulomb interaction with this manganese electron spin. So this was potential exchange for localized spins, but now go to, let's assume that we have no interaction of single electron with manganese, but now assume that we have only electrons in the conduction band. Yeah? What about electrons in the conduction band? Again, we can construct anti-symmetric wave function and convince ourselves that this interaction makes that electron prefers to be parallel. Electrons prefer to stay parallel because they never meet, and their Coulomb interaction is reduced. So we can say, okay, we have all materials should be ferromagnetic because electrons lower their energy because Coulomb interaction is lower if they are parallel. And why they are not parallel in sodium, gold? Because we have two terms in Hamiltonian, kinetic energy and potential energy. Potential energy is going down, but kinetic energy, if we polarize electrons, kinetic energy goes up. Yeah, electron redistributed, must redistribute to have all parallel spins, and the kinetic energy goes up. So competition between this lowering of kinetic energy, of potential energy due to polarization, and increase of kinetic energy. So we have this increase of kinetic energy described by this equation, where here is number of electrons in spin up and down, competes with this exchange energy, and this determines whether electrons are polarized or not polarized. And how we can calculate, this is not trivial, but in some case we can say, let's assume that only correlation which exists is due to this anti-symmetric wave functions. That only correlation which exists is the statistical forces which makes that electron with the same spin don't want to stay together. So this G goes to 0. This correlation function, this probability to find two electrons with the same spin at distance r, goes to 0 for r equals 0. And now it's -1 because we have to subtract interaction with the background, which we assume here homogeneous. So competing between these two is well-known this Bloch model of ferromagnetism. And if you do such calculation, you end up that actually material should be ferromagnetic if average distance between electrons comparing to Bohr radius is 5. But it turns out this is, in this range of theory, this assumption that only correlation induced by statistical forces count is wrong. Actually, we have to take correlation induced by Coulomb interaction. We have to take so-called exchange correlation energy properly. And if you do that, it's turns out this Bloch model does not work. Simply does not predict ferromagnetism. So ferromagnetism of iron cannot be simply explained like that. We can go to another model, which is very well known in literature, Stoner model, which is phenomenological model. We know that ferromagnetism exists. So how we can save this ferromagnetism in the same model? We can say, let's take this interaction as a constant, not calculate for Coulomb interaction, but because of screening, which the simple model neglects, of course, and this kind of things, we have a constant here. So we replace this interaction, Coulomb interaction, by a constant, actually. Fourier transform this interaction by constant. And then, if this constant is sufficiently large, we end up with ferromagnetism. But it's kind of phenomenological model. Always you can find a constant which, at given material, will explain you ferromagnetism. And normally what you should do, actually, it was what was explained in previous talk, you have to do usually heavy calculation, take multiband character of real metals, as decoupling, often spin-orbit interaction if you want to understand anisotropy and so on. So understanding of ferromagnetism of metals usually requires a lot of careful examination of band structure effects. Simple models are very beautiful to imagine why ferromagnetics come about, but actually it is a little bit more complex in reality. Okay, this was the role of potential exchange, which produces Hundruls, produces positive ferromagnetic-like exchange interaction between electron in the conduction band and localized spin in the localized spin on manganese ions, for instance, and so on. Now we go to another type of exchange, is kinetic exchange. So we said already this kinetic exchange comes about from term in kinetic energy. Something happens that if we change orientation of spin, kinetic energy of spins changes, of the particles which interact. So potential exchange, it was a good example to take quantum dots and two states in quantum dots, but to understand kinetic energy, exchange interaction, it's good to take two quantum dots. So now assume that we have two quantum dots. There is a certain barrier between these two quantum dots. So electron has difficulty to tunnel, but can tunnel a little bit. And what happens if electron can go here only if these two spins are antiparallel? Why? Because electron wants to go to lower possible states, and this lower possible state is, let's say, S state. And in S state already one electron exists, so second electron has to have opposite spin. So what you see that these two electrons can go to second quantum dots only if they are antiparallel. So the kinetic energy goes down if they are antiparallel, because if they are antiparallel, actually they reside in two quantum dots. The kinetic energy is lower because the localization is lower. If they have the same spins, they can go to second quantum dot by very high energy. This is a small probability. The hybridization is small, as we say. But if they have opposite spins, they can move from one dot to another, and the kinetic energy, the wave function is less localized, goes down. And this reasons that in hydrogen molecules, ground state is singlet. It's the same reason that if we have opposite spin, actually we have lower energy and the binding energy is higher, and therefore hydrogen atoms prefer to have to spin antiparallel, hydrogen atoms in hydrogen molecule. And the same happens in two quantum dots. And the same happens also if we have manganese spins and we have holes which reside, or we have carriers in the conduction band which reside nearby. Let's start from situation we have metal. We have Fermi level up to fill up electrons up to Fermi level. And you see that these electrons now can hybridize, can go to this D band. So assume we have metal, we introduce magnetic impurity, and once we introduce magnetic impurity, this electron from metal can hop to this magnetic impurity, so can delocalize a wave function. Yeah? And they can hop only provided that their spin is antiparallel to the spin of manganese impurity which we introduce. And we can think it's a little more complex. We have to analyze that this electron can hop if we make a hole, but all together actually make, this was shown by Schiffer, actually, that we have anti-ferromagnetic interactions, that this coupling due to kinetic exchange is anti-ferromagnetic. We have Kondo Hamiltonian, we say. That ground state corresponds that this carrier spin and this localized impurity spins are antiparallel, because only for such situation kinetic energy can go down, because this electron can delocalize, can be more delocalized in the absence of impurity or when spins are parallel each to other. And the same can be done, the same reasoning can be done to semiconductors, especially if we have valence band if we have valence band and now we introduce a hole to the valence band, we can ask the question how interaction with this d electron depends on orientation of the spins. And again, we end up with the same equation. I will not go into details, but physics is such that we end up with the situation that whole spin wants to be antiparallel to manganese spins. That interaction energy, total energy is lower if whole spin is antiparallel to manganese spin. So this is very important, and actually this presence of this coupling between holes and localized spins is behind of ferromagnetism of gallium manganese arsenide, Professor Hideono described this morning. And it was discussed also by Professor Sato in details. So remember this fact that holes can jump to this D level makes that hole want to be anti-parallel to manganese spin, and this is behind ferromagnetism of this material. But wait a while, how to understand ferromagnetism of this material? Now we only understand that single hole interact with manganese spins in actually strong way. That this interaction is quite strong. Why we know that it's strong? We can do magnetoptics experiments. For instance, we can look for splitting of excitons in various materials. And looking on splitting induced by magnetization, which we produce by non-zero magnetic field, we can see that the splitting, if we have very few holes, depends, this exciton splitting depends linearly on magnetization. And analyzing for experts, it is well known, analyzing various polarization, we can independently determine splitting of the valence band and of the conduction band. And from that, we can reconfirm that splitting of conduction band correspond to S decoupling, which is ferromagnetic, and the size of this is 0.2 eV, which is less than atoms by factor of 2. We understand that because electron sitting partly on anions, partly on cations, there is some screening. But if we go to holes, there is huge difference, factor of 5 at least. Splitting is much larger. In addition, the sign of this coupling is antiferromagnetic. So we have very strong coupling of holes, and this coupling is antiferromagnetic. But remember, now we speak about single hole interacting with many manganese. We do not discuss yet ferromagnetism. And we have actually, if we decrease distance between these anions and cations, this manganese spins, this goes up. These couplings go up, and actually a beautiful work was done here in Japan by Professor Fujimori group to prove this, that indeed if we go to lower and lower distance between cation and anions, this antiferromagnetic exchange coupling, its modulus here is antiferromagnetic, increases, and actually we can do this by photoemission, also we can do by exciton splitting, as I said. Okay, so this was this coupling of carriers with localized spins. Now we want to understand a little more ferromagnetism, how ferromagnetism come now in such localized spin system. And one thing I want to discuss is a situation where it happens, for instance, that we manage, like we can manage in manganites or other material. Imagine now that we manage to make material where we have two types of ions with different charge state and spin state. That part of our manganese, like in manganite, is 3+, another part is manganese 4+. How we do that? For instance, if it happens that this state resides in the band gap and we dop correctly, part of the electron goes to the bands or to impurity which we introduce, and we end up with some manganese being in different states than the other one. And now what we see, that now, if they have different two spin states, now there is no Hubbard energy. This electron can hop from here to here. Yeah? This electron can very easily hop. If there is the same charge state here and here, electron to hop must overcome this Hubbard energy. But if there is no electron here, this additional electron, this electron can just hop here. And therefore, this hopping is possible, provided that the spin are the same of these two localized atoms. If there is the same spin, electron, this fourth electron can hop here. Yeah? So you see that the kinetic energy also here, delocalization will be larger for ferromagnetic arrangement of these localized spins. Yeah? So double exchange come about from the fact that only for ferromagnetic arrangement, this electron can hop between these localized spins. Yeah? And we have two different charge and spin states of these localized spins. So this is double exchange. And it happens in manganite. It corresponds to TC about 300. That somehow we dop manganite, we replace this manganese, we replace this trivalent lanthanum by divalent valence 2 strontium. So there is one electron missed, and this electron is taken from manganese, and we end up with 2 charged states, and this reason for ferromagnetism in manganites. And now I have 10 minutes, 5 minutes, okay? So we go to indirect interaction. We go now to the situation where we have localized spins, and we ask the question, what happens if these 2 localized spins have the same spin and charge state, and especially in semiconductors and isolator, what makes that these 2 spins are coupled? Usually we have compound, semiconductor compound or oxide or something like that. Overlap between D wave function is too small to produce any interaction between these 2 spins. So there is indirect interaction which uses that something is between. And something in between could be either free carriers, or it could be this orbitals which are filled up with electrons. So let's start from that we have certain concentration of carriers in the conduction band, for instance. And what happens if we have certain concentration of carriers in the conduction band? Then if we have polarized, localized spins are polarized, then there is splitting. Yeah? There is splitting. And we said that this action of these polarized spins on electrons can be regarded as molecular field. So if we have this polarization, ground state correspond to splitting, like in electrons in the magnetic field. Electrons in the magnetic field don't stay unpolarized, start to be polarized. There is a redistribution of carriers between spin subband. But in our case, this field is produced by polarized manganese spins. But why we do not have often, not all the time, ferromagnetism? Because this lowering of energy when we have localized spins and interaction with localized spins, this lowering of energy associated that these carriers, electrons, are redistributed and use better the presence of polarized manganese spins, it must compensate increase of free energy associated with entropy. That polarized spins are more ordered, has lower entropy, and as we know, many body system does not like high entropy state, low entropy state, prefers high entropy state, disordered state, because disordered state can be organized at given temperature in various ways. So probability to find disordered state is greater at not zero temperature. So competition between this lowering of energy associated with interaction with localized spins must compensate this increase associated with ordering of spins. And this can be calculated also for complex band structure, like for holes in gallium manganese arsenide. Now we switch to the case of holes in gallium manganese arsenide, but physics is the same. We induce by presence of localized spin splitting of the valence band, but now we have to take very precisely all subtleties of the valence band, spin-orbit interaction, multi-band character, and so on, and then we end up with formula for TC, which contains here, it was shown by Professor Ono here, density of states, this coupling constant square. If we have lower dimensionality system, also it's quantum well width or cross-section of the wire, and contains enhancement of coupling due to the Stoner mechanism we discussed. And it is proportional to number of localized spins we have, of course. And we could also maybe take super exchange, I will discuss in a second. So we can calculate that numerically, because here is density of states, spin density of states for spin excitation, which takes into account this complexity of the valence band into account. And maybe we should come here. What is with this formula? We see that coupling constant square appear and density of states. Density of states will be large for holes, more for electrons, and also this coupling we said is much lower for electrons than for holes. So if you do measurements in zinc manganese oxide with aluminum, N-type, you end up with TC, which is as low as 160 milli-K. Yeah, because we have 5 times smaller coupling, square 25, we have lower effective mass. Altogether, we have 160 milli-K. If we go to P-type material, where coupling is higher, we have temperature which reaches 100, well, it's not now 190 people believe one can get. But anyhow, it's of the order something like which is kind of 3 orders, which is 3 orders of magnitude higher than in case of n-type. Yeah, we have instead of 160 milli-K, we have 160 K. And this can actually be explained here, theory, and this 160 milli-K can also be explained. So this was the Zener model, which simply corresponds. And now only I will say that it's the same, maybe in literature you saw RKKY model. I would say that it's just the same as RKKY model. It's different way to calculate, and especially in semiconductors, one can demonstrate that numbers which come out is the same. In RKKY model, you use second order perturbation theory to calculate the coupling mediated by 3 carriers. And this coupling oscillates as a function of the frequency, but if we have a dilute system, much less electrons that spins, in semiconductors okay. In metals, when we have more electrons that spins, it's not okay. And I only will say that in addition of that, we have super exchange. We have this antiferromagnetic super exchange, which we can imagine that we have bands which are totally occupied. We have bands which are totally occupied by electrons, and we have 2 exactly the same magnetic impurities. For instance, manganese 5/2. And now we have coupling between these electrons in the bands and this manganese. And please note that we can form, if we have anti-parallel orientation of the spin, we can make that this electron deform wave function becomes deformed of these electrons or holes in the valence band. Electrons, sorry, we have totally filled up bands, so we have electrons in the valence band. This electron can approach this spin and use this antiferromagnetic coupling which exists, and this electron can move here and use this. So it's kind of higher order effect, but makes that actually if this electrons deform, this one move here, another move here, we can win provided that these are anti-parallel. You see that if they are parallel, we cannot use this lowering of energy associated with this hybridization between this electron and this d shell. So usually the super exchange, not always, but usually is antiferromagnetic. That actually we have bands which are totally occupied. This indirect interaction mediated by the valence band is antiferromagnetic, because then we can use this hybridization only if they are antiparallel. So this second order process, and as I said, in some cases we should take into account that it can be ferromagnetic. So summarize, we have potential exchange, which we discussed for localized states, and Hund's rule and coupling between S electron, D electron comes from that. In case of extended state, it leads to ferromagnetism, which we discussed 2 models, but actually we mentioned that these models has to be replaced by more accurate calculation. Then we discussed kinetic exchange, saying that it leads to Kondo Hamiltonian. Then it was double exchange, and manganite, very important. It operates if we have 2 different charge states, spin states. And then we discuss indirect coupling, how presence of bands affects coupling between localized states. And we said that we have 3 carriers. We have in semiconductor ferromagnetic coupling, which can be described in 2 ways, either by Zener model or RKKY models. This gives the same. And also we mentioned that we can have, via polarization of bands, can have the super exchange of, sometimes people call part of the super exchange, Blomberger-Rowland mechanism. Thank you very much.